We're now going to take a look at some more special graphical features of lines or linear relations in order to continue our warm-up in our study of relations by looking at this familiar type of relation. So we'll be looking at a number of sort of special linear properties here. These are geometric properties or graphical properties of lines that are special enough to be distinguished with vocabulary and so on. We'll consider the idea of a horizontal line and kind of alongside that, a vertical line. We will look at when two lines are parallel and when two lines are perpendicular to each other. And the point of all of this is to see yet again that these graphical properties of lines can be identified using analytical representations of those lines. In other words, we can see from the equations of the lines that they have these features without having to actually look at the graphs. So this will develop our ability yet more to understand how the same relation can be represented both graphically and analytically. So we'll tackle each of those four properties in turn, beginning with horizontal lines. Let's start by defining what a horizontal line is and seeing how to recognize one. We'll again begin with a graphical definition of a horizontal line. We'll say that a line is horizontal if it moves or proceeds to the left and to the right without ever moving up or down. So here's a little illustration. The blue line that you see here is a horizontal line. Notice that it only goes left and right. It doesn't move up or down at all. So let's take this graphical definition and translate it into an analytical definition. And our tool for doing this will be the concept of the slope of a line. So the key thing to observe here is that if a line only moves left and right and never moves up or down, then no matter where we go on the line, if we move between 2 points on the line, the y coordinate stays the same. So when we're calculating our slope, y2 minus y1, the thing in the numerator of the slope formula, will be 0 because y2 and y1 will be the same. That means that the whole line will have a slope of 0. Since when you have 0 divided by a number, you get 0. So that allows us to transform our graphical definition of a horizontal line into an analytical one. We can say that a line is horizontal if its slope is 0. And from there, we can draw a further conclusion. If you have a horizontal line, an equation for it can always be written in the form y equals y1, where y1 is the y coordinate that every point on the line shares. So you can figure out often just by looking at an equation for a line that it represents a horizontal line, because only y will appear in the equation. You'll have an equation like y equals 4, y equals -1, y equals pi, something like that. Y equals a constant. X doesn't need to appear because if you go to one of our linear equation forms, if m is equal to 0, x will end up not mattering. So that is a way to take our graphical characterization of a horizontal line and transform it into an analytical one. We now know what the equation for a horizontal line looks like, or at least one type of equation for a horizontal line. Let's turn them to vertical lines, which are similar. We'll do the same thing. We'll start with a graphical definition and then translate it into an analytical one. Here's our graphical definition. We can say that a line is vertical if it proceeds up and down without ever moving left or right. So here's a little illustration. The blue line in the graph you see here is a vertical line. And we'll do the same thing. We'll take this graphical definition and adapt or modify it into an analytical one. The key thing to observe here is that in a vertical line, if you're only moving up and down and never moving left or right, all of your points will have the same x coordinate. And that means when you go to calculate your slope, the thing in the denominator of the slope formula, x2 minus x1 will be equal to 0 because, again, x2 and x1 will be the same. This means, since we're now talking about 0 in the denominator of a fraction, that the slope of the line will be undefined. In other words, there will be no number we can assign as the slope of a line. So there's an analytical definition of a vertical line. A line is vertical if its slope is undefined. Let's see how that, or what effect that has on equations of vertical lines. One quirky thing about vertical lines is we can't write their equations in either of our two familiar linear equation forms, point-slope form or slope-intercept form. The problem is that both of those equation forms require something to go into the m place, the slope place in the equation, and we don't have anything to put there. There is no slope to plug in for m. But again, if we have a vertical line, any 2 points on it will have the same x coordinate. In fact, all of the points will have the same x coordinate. So the one thing we know about any point on a vertical line is its x coordinate. And that means that we can use an equation of the form x equals x1 to represent the line. Where x1 here is a constant, it's the common x coordinate of every point on the line. So here's one example. The equation x equals 2 would represent a vertical line, the line going up and down through all the points that have 2 as their x coordinate. That's 2 of our 4 special linear graphical properties. Let's turn now to parallel lines. We'll do the same thing. We'll define what parallel lines are graphically and then transform that into an analytical characterization. Here's our graphical definition. This is about 2 lines now. Being parallel is kind of a relationship between 2 lines. We can say that 2 lines are parallel if they never intersect, no matter how far they're extended in either direction. So here's another kind of simple illustration. We have a blue line here and a red line, and these are parallel lines. No matter how far you bring those lines out further, keeping them moving in the same direction, got to be straight lines, they will never intersect each other. So they are parallel. Now here's an analytical definition. We won't go through all the steps required to figure out that this works, but it does. And it has the features we want of an analytical definition of something like this. 2 lines are parallel if they have the same slope, but pass through different points. Now notice here, this analytical definition is a good deal more, we might say, precise. It can be hard to tell if you're looking at 2 lines, looking at graphs of them. It's hard to tell sometimes whether they're really parallel. It might be that they are almost parallel, but if you go out far enough, eventually they intersect. It just takes a long, long, long time to get there. But if we have 2 linear equations, it's very easy to figure out whether the slopes of the lines that they represent are the same, as long as you know how to get the slope out of the equation, which we know how to do. So let's look at an example. We'll figure out whether 2 lines are parallel. And we'll do this by using analytical methods. So here are 2 linear equations. We have 2x plus 4y equals 7 on the left, and 6y equals negative 3x plus 2 on the right. So those are 2 equations. They're both linear equations. Neither one of them is in either of our standard forms, though. And in this case, we'll use slope-intercept form. It's going to be a little easier here. And we're going to rewrite each equation into slope-intercept form. The first equation can be put into slope-intercept form. We'll start by subtracting 2 from both sides of the equation, or sorry, subtracting 2x. I'm going to keep the other equation the same for now. And now in our first equation, I'm going to divide everything by 4 in order to undo the multiplying by 4 that's happening to y. So we get this, y equals negative 2/4 x plus 7 over 4. I'm going to do something similar in our other equation, except now I'm going to divide everything by 6, since in this equation, y is being multiplied by 6. And our goal here in both equations is to isolate y, to get it all by itself on one side of the equation. We're pretty much done. The only thing I'm going to do is to simplify a little bit by reducing some of the fractions that you see. So in our first equation, -2/4 can be reduced to -1/2. In the second one, -3/6 can be reduced to -1/2, and 2/6 can be reduced to 1/3. That says 7 there. It should say y. That's a typo. I apologize for that. The key thing to note, though, is that now both of our equations are in slope-intercept form, and we can easily see by looking at the equations what the slopes are. In both cases, the thing in the m place, the coefficient of x, is -1/2. Since the two lines have the same slope, we can conclude that they are parallel lines. Oh, the other thing we want to note here, they not only do they have the same slope, but they have different y-intercepts. The y-intercept of the first one is where y equals 7/4. The y-intercept of the second is where y equals 1/3. If those y-intercepts were the same, the lines would go through exactly the same points, and we would really only have one line. But since our lines go through different points, these are two different lines with the same slope, so they are parallel. Finally, let's take a look at the idea of perpendicular lines. Again, we'll start with a graphical definition. We'll say that two lines are perpendicular if they intersect at right angles. So here's a little illustration. Again, we've got two lines, a blue one and a red one, and the point where they intersect creates 4 right angles. Those angles made by the lines are right angles. Here's an analytical definition. We can say that two lines are perpendicular if their slopes are opposite reciprocals of each other. There's some vocabulary we need to recall here. Remember, reciprocal refers to what you get if you take a fraction and flip it upside down. So if you have 3/5 and you flip it upside down and you get 5/3, those are reciprocals. But we want opposite reciprocals. Opposite in this case means you stick a negative sign in the front, or if there's already a negative sign, you take it off. So if we have a line with a slope of 3/5 and another line with a slope of -5/3, those two numbers are each other's opposite reciprocals, so the two lines will be perpendicular. Let's look at an example involving perpendicular lines. Say that we've got one line. So we're trying to find an equation of a line. We know that the line has the point 1, -2 on it, and we also want our line to be perpendicular to the one represented by the equation x + 3y = 6. So our goal is to find an equation for the line being described here. Now, to do this, we're going to need two pieces of information. We need the slope of the line, and we need the coordinates of a point on the line. If we have those two things, we can write an equation in point-slope form. Now, we're already given the point. The point 1, -2 is on our line, so we've got a point. To get the slope, we need to use the fact that the line we want is perpendicular to x + 3y = 6. So the slopes of these two lines will be opposite reciprocals, which means if we find the slope of x + 3y = 6 and take its opposite reciprocal, we will get the slope of the line we're looking for. We'll find the slope of x + 3y = 6 by putting the equation into slope-intercept form. So this will be similar to what we did in our last example. There's the equation we're starting with, and we want to isolate y by doing some algebra. I'll start by subtracting x from both sides of the equation, and then I'll divide everything by 3. This is what we get. Y = -1/3 x + 2. So we can see that this line here, the one represented by the equation we were given, has a slope of -1/3. The opposite reciprocal of -1/3 is 3. Take off the negative sign, that gives us the opposite, and then flip the thing upside down. 3/1 is equivalent to 3, and so 3 is the opposite reciprocal of -1/3. That means that the line we're trying to find has a slope of 3. We now have everything we need to write an equation for our line. We know the point 1, -2 is on the line. We know the line has a slope of 3. Here's an equation for it in point slope form. Y plus 2 equals 3 times x minus 1 represents our line. We could put that into a different form if we wanted to, slope-intercept form or something like that, but why bother? We have a perfectly good equation here in a standard form. We'll stick with that.